Welcome! In today's lecture, we will cover the first part of Chapter 21, where we will discuss enols and enolates. To begin with, let's take a look at this ketone. We can describe the position of the carbons and the hydrogens near the ketone using Greek letters, and this is going to describe their proximity to the ketone based on the carbon atoms. So the carbon atoms directly next to the ketone will be the alpha carbon, and the protons attached to the alpha carbons will be alpha protons. And as we move further away, we'll have beta, gamma, and delta. In this chapter, we're mostly going to be focusing on chemistry of the alpha carbon. We'll be learning new ways to make bonds at the alpha carbon. The most common reaction that we can use with the alpha proton is the interaction between a ketone or an aldehyde and its enol and enolate. And this reaction should be slightly review, as we've done some examples like this in class as well as in lab, but in this chapter we're going to cover this reaction more thoroughly. In the presence of a catalytic acid or base, a ketone is in equilibrium with its enol form. And if we then undergo a reaction with the enol, we can form a new carbon bond at this position. In the presence of a strong base, we can deprotonate at the alpha position and form the enolate, which is an even more reactive intermediate. In the presence of an acid or a base, a ketone or aldehyde is going to exist in the equilibrium with its enol form. These are called tautomers of each other. And for most ketones or aldehydes, the equilibrium is going to greatly favor the ketone. But there will always be some percentage of the enol tautomer that exists. And depending on the specific substrate, some will have a higher percentage in the equilibrium, in the enol equilibrium, than the ketone equilibrium. For example, this 1,3-diketone is actually favored to be in the equilibrium where the enol is the major tautomer. And this is due to the stabilization of hydrogen bonding of the alcohol that's formed in the enol with the ketone next door. So in this case, we'll actually see 70 to 90% of the molecule in the enol form. Another example of a molecule that has a favored enol form is that of a phenol, where aromatic stability is a factor. So in this case, the enol has a benzene ring, and it's stabilized by the aromaticity of the benzene ring. In order to form the ketone, aromaticity must be broken, and so the equilibrium is going to lie very far to the right in this example, forming phenol. Let's take a look at the mechanism for the keto-enol tautomerization. And just like last chapter, we will have a different mechanism depending on if the reaction or if the molecule is in the presence of acid or in the presence of base. In acidic conditions, the first step of the tautomerization mechanism will be a proton transfer to protonate the carbonyl group. This is then going to allow a resonance stabilized cation to form, and after a deprotonation of the alpha hydrogen, we can form our enol. In basic conditions, the order changes. Our first step is going to be a deprotonation of the alpha hydrogen, and then in the second step, the resonance stabilized anion, we can push the electron density up to the oxygen, which can then be protonated to form the enol. Now, this is probably one of the most important slides, because really what we're going to be looking at in this chapter is the chemistry at the alpha carbon here, and we're going to be looking at the alpha position of an enol as being nucleophilic. So if we look at this structure here, we could see that we have a full-blown negative charge on the alpha position, and so this is a new form of nucleophilic carbon that we will have available to us. In the presence of a strong base, we can form an enolate, and so this enolate anion is going to be an even more nucleophilic version of carbon than an enol because it carries this negative charge overall. So a resonance stabilized enolate anion is going to be a very strong nucleophile at the alpha position, a nucleophilic version of carbon. This nucleophilic version of carbon can actually undergo two different types of reactions, depending on which resonance structure we use or which form we use. So if we have the negative charge on the oxygen, then we can undergo the oxygen doing attack, the oxygen acting as a nucleophile and forming a new bond with an electrophile. And if we have the negative charge on the carbon in the enol, then we can, in the enolate, then we can undergo carbon attack of the electrophile. And this carbon attack of the electrophile is the most common and will be the mechanism for the majority of the reactions that we're going to look at in this chapter. So we have the alpha protons, the beta protons, and the gamma protons. For the most part, we're only going to be looking at chemistry at the alpha proton for this chapter. The alpha protons are acidic because they have the ability to form this enolate. They're actually more acidic than just a normal carbon-hydrogen proton, but the beta and gamma protons are not acidic. And we can look at the pKa of a variety of ketones and aldehydes, and you notice that the pKa of the alpha proton is much more acidic than our standard sp3 carbon-hydrogen bond. Normally we're looking at pKa's in the 40s to 50s for a carbon-hydrogen bond, but in the alpha position, our pKa drops down almost to 16 to 20, which is fairly close to the pKa, for example, of water. When the pKa of the base is similar to that of the pKa of the alpha proton, then the equilibrium will have both the protonated and deprotonated forms existing. In order for us to irreversibly create an enolate, then we're going to need to use a stronger base. And there are a few common bases that we use for this. LDA is the most common, lithium diisopropylamide. This is a very bulky nitrogen molecule. We have two isopropyl groups on the nitrogen, which means that it's not going to be nucleophilic because of the bulk, and it'll be a strong base as well. And we can form this by reacting diisopropylamine with N-butyllithium. When LDA is used to form an enolate, the amount of ketone present at the equilibrium will be very little. So we can almost think of this reaction as a forward reaction instead of an equilibrium reaction. When we have a alpha proton that is doubly alpha, it's going to be much, much more acidic, and that's because of this increased stability of the enolate that we saw in the acetylacetone example. So here we have a pKa of just 9 compared to a pKa of up to 17. In fact, 1,3-dicarbonyls are acidic enough that we can irreversibly deprotonate them with alkoxide because we've now made the proton 7 orders of magnitude more acidic. So for a doubly alpha proton, we only need to use a alkoxide anion. So depending on the type of enolate that we'd like to form, we will use different bases based on different reactions. For example, if we want both the enolate and the ketone to be present in equilibrium, we can use sodium hydroxide or sodium ethoxide. But if we want to irreversibly form the enolate, then we should use sodium hydride or LDA. For a dicarbonyl, we do not need to use LDA. So the first alpha reaction that we're going to look at is halogenation. So we can take an enolate or an enol and form a new bond, carbon halogen bond at the alpha position under the conditions of acid and bromine. And so this will work with chlorine, bromine, or iodine. And since we're in acidic conditions, right, this means that we're going to be using the enol as the reactive intermediate. So we could take a look at the mechanism for this. The first step is the formation of the enol, where we protonate the ketone, and then we can have another proton transfer occur, which leads us to the enol. Once the enol is formed, we'll collapse the electrons back down to reform the carbonyl, and the electron density from the enol acts as a nucleophile. Remember, we have a nucleophile now at the alpha position. We're forming new bonds with the carbon at the alpha position. We'll form a new carbene-bromine bond, and a bromine-bromine bond will break. After a proton transfer step, we will obtain the brominated product. When we want to think about regioselectivity, we're going to have to take a substituted product, so an unsymmetrical ketone. In this case, there's two potential products. We could brominate at the less substituted side, or we could brominate at the more substituted side. And what we will find is that the bromination at the more substituted side is the major product, and this is because we're going to form the more stable or more substituted enol, and then this enol will then go on to be brominated to form this product. And so this allows us to obtain a two-step synthesis for alpha-beta unsaturated ketones. And the reason that we're bringing this up right now is because this is going to be an intermediate or a starting material in some reactions that we'll look at in the future. But in this case, under acid and bromine, we'll brominate in this position, and then a strong base allows us to do an elimination, which gives us the alkene in this position, or an alpha-beta unsaturated ketone. And so we can use any of the bulky bases that we've learned for this deprotonation. If we use a non-bulky base, right, it would form the alkene up in this position. The next reaction we'll look at is a named reaction, the Hell-Volhard-Zielinski reaction, or the HVZ reaction. And this reaction is going to brominate at the alpha carbon of a carboxylic acid. We take a carboxylic acid and treat it with bromine and PBr3, and then water. And so the mechanism is believed to be the following sequence, where the PBr3 first forms an acid halide, and then the acid halide equilibrates to its enol form, which can then undergo bromination, and then water will reform the carboxylic acid from the acid bromide. We can also do alpha bromination or halogenation under basic conditions, and this would go through a different intermediate. In acidic conditions, we're going through an enol intermediate. In basic conditions, then we're going through an enolate intermediate. And so our hydroxide anion deprotonates to form the enolate, and then the negative charge on the carbon will then attack the bromine with the bromine as a leaving group. Since our enolate is more reactive than an enol, this reaction will proceed fast enough that we're going to obtain polyhalogenation. So once the ketone is brominated once, then another molecule of base can deprotonate the second alpha proton, and then we will obtain a second bromination. Under basic conditions, we can react sodium hydroxide and a halogen to form, in the haloform reaction, to form a carboxylic acid. So this is a way that we can convert a ketone to a carboxylic acid. And so our mechanism here is we're going to first brominate using the sodium hydroxide and bromine. We're going to brominate this position 3 times using the previous mechanism that we saw. And then at this point, we have a good leaving group. The CBr3, because of the amount of electronegativity of those 3 bromine atoms, becomes a very good leaving group. And so then our hydroxide can attack, and then the ketone electrons will eject that CBr3. After the CBr3 is ejected, it can then deprotonate, and we have the carboxylate anion. After we form the bromoform, this switches us from being in equilibrium to now a non-reversible arrow. So for this reaction, we can use bromine, chlorine, or iodide, and this is a synthetically useful way for us to convert a ketone into a carboxylic acid. If an aldehyde is present when an enolate is formed, the enolate can attack the aldehyde, and this will result in an aldol addition. So we have ald coming from the aldehyde and all coming from the product. The product features both the aldehyde and alcohol functional groups. So we can take, for example, formaldehyde here, and in the presence of sodium hydroxide, an enolate will form on 1 and form this 1,3 product. So under basic conditions, we can look at the mechanism of this reaction. First, we have alpha position deprotonated, which then allows the enolate to form. Now we have a carbon nucleophile, and the aldehyde itself is a carbon electrophile. So the carbon nucleophile can then attack the carbon electrophile, forming a new carbon-carbon bond, and the reaction is finished with a proton transfer. For most of these, we're going to have an equilibrium process, and in many cases, for simple aldehydes, the aldol product will be favored. So for example, butanaldehyde will have 75% as the aldol product, and 25% in equilibrium will be the aldehyde. However, for ketones, the aldol product is not favored. Instead, the starting material remains favored. We can also undergo the reverse process because this is an equilibrium reaction. So in the reverse process, we deprotonate the alcohol, and then the electron density on the O- pushes down to reform the carbonyl group and breaks the carbon-carbon bond. At this point, we can have a proton transfer to return the ketone. When we have an aldol product that is heated under acidic or basic conditions, then we can have an elimination reaction occur. So under acid or base, depending on which, we will get an elimination, and this will result in an alpha beta unsaturated ketone, or the aldol condensation product. And it's named a condensation because we're releasing water as our byproduct. This aldol condensation will occur when the aldol addition reaction is performed at elevated temperatures. So an aldol addition will form a beta hydroxyaldehyde, or a 1,3 relationship between the ketone and the alcohol, or the aldehyde and the alcohol. And if this is then heated, an elimination reaction will occur, which leads to the alpha beta unsaturated aldehyde. Let's go through the addition of this aldol condensation mechanism. First, we have a proton transfer, or deprotonation, to form the enolate, which then undergoes nucleophilic attack, forming our new carbon-carbon bond. A proton transfer will then result in the aldol product. Next is the elimination of water. So we have another deprotonation occurring, which will put a negative charge on the alpha carbon. This negative charge can then collapse and eject hydroxide to form our aldol condensation product, and this will be under basic conditions. There are two potential stereoisomers that are formed in an aldol condensation, since we are forming an alkene, and the trans isomer will be the major product, as it is more stable with less steric interactions. In many cases, it's impossible to actually isolate the aldol addition product because the aldol condensation will occur. In these cases, we'll have a large amount of the material form the aldol addition, aldol condensation, and only a small amount forming the aldol addition. And if we have a product that is a poor reactant for the aldol addition, like this ketone, at 10 degrees Celsius it only has 20% yield, we can heat up the reaction and then we'll obtain the elimination aldol condensation product up to 90% yield.